Right, we're back to GCSE, and the funny thing is, I think most GCSEs have actually finished, and some students have already received their grades, so I'm way behind on this. But whatever, let's keep going. I've got um, biology, chemistry, electronics, and geography to get through, so I'm going to do electronics now. So I looked this up, and to my disappointment, in 2017, electronics was removed from AQA and EdXL, which are the two main examining boards, which means a lot of schools won't be doing electronics anymore, which is a shame because electronics is it's the future. More schools should be doing it, not fewer. But apparently the exam boards know better about what technology needs. Nevertheless, it is available on Educas, so they still run it, but that just kind of narrows the availability to schools. So, um, it's okay. Let me start filling this in. It was a really good subject. I really enjoyed it. It uses a bit of maths, even a bit of calculus at A level. I don't think it uses calculus at GCSE. And you learn how to make electronic circuits. You learn how to do signal processing, um, even programming on a very, very basic level, like assembly language programming for microprocessors. Although a lot of that came in A level, GCSE was a bit more basic. Calculator and a ruler. Oh, yeah, well, I'll use Google for the calculator. So we have an information sheet here. Oh, and let's turn that off. So I'm predicting a 7 for this because I don't remember half this stuff. But I might do better. So resistor color codes. I could never really do this because I'm colorblind, so some of these colors just merge together for me. And then you've got tolerance levels, resistors, useful equations. Oh wow. I don't recognize half of these. Okay, De Morgan's laws. Um, oh man, I don't. What is this? I don't know. Ooh. Okay, this one here is like harmonics. It's like parallel resistors in parallel something. I don't know. Current in parallel. All right, let's hope they're gentle with us. Let's begin. Come on. There we go. All right, the diagram shows the pin for an IC, integrated circuit. Label pin 1 and pin 14 on this IC. I think this is the top. That's the top left, that dot there. Hang on, is my mouse appearing on the screen? Let me just make sure. Yeah. Okay. So I think this is 1 and this is 14. How many logic input pins in total are there on this IC? 1, 2, 3, 4, 5, 6, 7, 8, 9. Logic output pins. 3. Name the type of logic gate found on this IC. So this is, so without dot in front of it, without the circle in front, it's an OR gate, I think. Yeah. So this is a NOR. Draw the logic gate symbol for an OR gate. Just a bit pointier at the end. That's fine. NAND gate. It's like this, right? And put that to make it NAND. Oh, don't forget the pins. Probably need the pins. Complete the following truth tables for an AND gate. So it's 1 when both inputs are 1. A NOR gate. So an OR gate would be 1 when either pin is 1. So a NOR gate would be 1 when neither pin is 1. Neither input is 1. For each of the subsystems below, state if they are input, process, or output subsystems. Output, input, transistor switch unit, process, I guess, comparator, process. Kew Gardens in London. I've never been there. Or seen it. The world's biggest Victorian glass house. Automatic watering system. The watering should only operate at night. The watering system should operate only when the soil is dry. So it's dark and dry. The water flow is controlled by a solenoid valve requiring a current of 4 amps to operate it. The water should be turned on for a fixed period of 15 minutes. Oh my god. The moisture sensor outputs logic 1 when dry. The light sensor outputs logic 0 in the dark. The temperature sensor outputs logic 1 when hot. Well, we don't care about the heat, do we? So we want 1 when dry. So it's moisture. Light. Not. So that means we'll get 1 when it's dark. We need AND. So that triggers temperature sensor. Alright, so we've used moisture, we've used light, we've used not and. I don't think we need temperature at all. I think they're tricking us. Delay unit? So we need 3 things here. I would say, so we need delay unit, then solenoid unit. What's a latch unit? Alright, solenoid is the last thing, because that triggers the water. solenoid. So what, the last two? Delay unit, certainly we need that. But latch unit? What is a latch unit? I don't think you need the others, so let's say we need a latch unit and a delay unit. My guess would be latch stabilizes it. So because the light, as soon as the light is just dimming, it reaches a point where it might be flicking on and off this switch because it can't tell whether it's hit the threshold or not. So a latch would basically give us a hysteresis, I would hope. Delay would delay unit monostable? Does that mean we do one on period? I don't know. The following circuits contain identical power supplies and lamps with a different combination of resistors. In which of the three circuits will the lamp be dimmest? So the most resistance is probably here. When you put resistors in parallel, there's less resistance overall because there's more ways for the current to travel. So it should be B. More resistance equals lower current. Diagram shows part of a circuit. Determine the values of the following. V1. Well, V2 is 3 volts because the voltage across R2 is 3 volts, therefore it must be the same for V2. So that's 3 volts. So then V1 must therefore be 6 volts. I1 is V over R. So 3 over oh wait, we don't know the resistor. So that's 25 milliamps, so we've got 10 milliamps there, therefore it must be 15 here. The current sum. I2 must be 25. Calculate the value of R2. So R2 would be V over I. So it would be 3 volts divided by 10 milliamps. 3 volts divided by 10 milliamps. Let's make sure we write this all out. R equals V over I equals 3 volts over 10 milliamps equals, let's just write this out so it's clear. Amps equals 300 ohms. What is the color code on resistor R1, which has a tolerance of plus or minus 5%? I think plus minus 5 is gold. Let me check. So we got. Oh, I should have checked the amount first. color code on resistor R1, which is a tolerance of 240 ohms with a tolerance of 5%. So it's gold, 240 ohms. Do you just do red, yellow, black? What if you want bigger? Red, yellow, black. Let's go with that. Red, yellow, black. Simple 6 volts power supply to operate from a 12-volt battery shown below. Okay. The circuit is tested by connecting a 200 ohm load across the output. The output voltage is now less than 6 volts. Explain why the output voltage is less than 6 volts. Let's use a text box for this. Where's my... Connecting resistors in parallel reduces the overall resistance across the pair of them. According to the law of resistors in parallel. So the combined resistance must now be less than 200 ohms. 1 over 1 in 200 plus 1 in 200 equals 100 ohms. Since this is because the current splits evenly between the two paths. So by V equals IR, the voltage across one must reduce. Okay. Wait, the new output voltage. Okay. So current overall current equals V over R equals six volts across 200 ohms. 6 volts across 200 ohms equals V over 100 equals 30 milliamps. Current across new load equals 30 milliamps over 2 equals 15 milliamps. So what were they asking for? New output voltage. V equals IR. V equals IR equals 15 milliamps times 200 ohms. Is that right? Yeah, I guess so. So it'd be 3 volts. Draw a circuit diagram below to provide a regulator. I mean, the amps, I didn't need to calculate the current. I already established before it's going to halve. The current is relevant. Draw a circuit diagram below to provide a regulated power supply for the 200 ohm load resistor using a 6.1 volt Zener diode. Oh no, I don't remember Zener diodes. I think they look like that or something. I don't know. They have a line through them, something like that. No, not like that, but could be something weird like that. I don't know. 200 ohm load resistor using a 6.1 volt Zener diode. Can we not just... So can we not just do the Zener diode? I don't know the symbol. And then a resistor? So it will spend 6.1 volts and then it'll have like 5.9 here. Do we need 6 volts? I don't know. The student has designed a system to close a ceiling blind in a conservatory when it becomes too bright outside. The blind should close when the light level is 400 lux. The comparator output is high. The solution is shown below. Evaluate the circuit design and determine whether it is a suitable design and describe any modifications required to meet the specification. Oh my god, 6 marks. Oh no. Oh no, 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 no. So let's have a look at this. What do I know? That would be 4.5 volts. Blind should close when the light level is 400 lux. So when it's lux, 400 lux, we get 25 kilo ohms. That's not right. Well, we want R1 should be R1 should be 25. And when it's lower, so we want blinds to close. I'm gonna close the blinds when it's bright. Okay, so when it's higher than 400, the resistance will be lower. So there should be lower voltage. So there's two problems here, I think. One, the input's the wrong way around. So when light is higher, R2 resistance decreases, which decreases the voltage on plus input pin to comparator. This is the opposite of what we want. Instead, the inputs to the comparator should be swapped. This would result in higher lower voltage on the pin in brighter light, which would trigger the positive output on the blinds mechanism. Alright, so that's the first problem. The fixed input to the comparator it is currently 4.5 volts. At 400 lux, the switching point we want, the resistance of R2 is 25 kilo ohms. It is expected to be 25 kilo ohms. at this point, we would want 4.5 volts to be across R2, which would match the other input and therefore be a suitable switching point. This is currently not the case. We need R1 to be 25 kilo ohms for this to correctly switch at 400 lux. Alright, what else? Otherwise it's good, right? I mean, with these two fixes, the circuit would work correctly and is a suitable design. Alright, that's all I can say. Diagram below shows a logic system. Write down in terms of the inputs A, B, and C, the Boolean expressions for output D. D is not A. Output E, so it'd be B and C. B. What do we use? Is it B? Let's have a look at this formula sheet. I don't know what symbols we use here again, because it's different in every field. It'd be A time dot B, I see. Is dot and plus in this field. Dot C. I'll put Q. So it'd be A with plus B dot C. Hang on, there's no room for this. So we've got A plus B dot C or we can use De Morgan's laws, but whatever. Complete the following truth table. We could actually just use De Morgan's. So if you do that, you'd get A dot B plus C. Is that how it works? Complete the following truth table for this logic system. Oh dear. Okay, so D is not A. So it's 1 0 1 0 1 0 1 0. E is B and C. So 0 0 0 0 0 0 1 1. And Q is D nor E. So 1 here, 1 here, 1 here, 0 elsewhere. Redraw the logic circuit using NAND gates only. So ultimately Q redraw the logic circuit using NAND gates only. So Q is so NAND. So AND is 1 when their inputs are both 1, 0 elsewhere. So NAND is 0 when they're both 1. 1 otherwise. You can make anything out of NAND gates, and you can make anything out of NOR gates. Like a NOT gate is just a NAND gate where you... So I can turn D into NAND gates, I can turn E into NAND gates. How do I turn this? Do we need to do this though? Let's have a look at Q. Maybe there's an easier way. So it's... So NAND is 0 when both inputs are 1, and 1 otherwise. So right now we have 1 either when it's 001, 011, or 101. So we need A to be 1. And C and B to not both be 1. That's the rule. A is 1. C, B, and not both 1. So if I did B and C into a NAND gate, it would be zero when they're both 1. Hang on, yeah. Yeah, it'd be 0 when they're both 1. So now what we want is... It's 1 when A is 1 and B is 1, isn't it? Yeah, and this input is 1. So we want AND. So we want this and this. So it's just that. Does that work? Ah, let's look at our De Morgan laws. That actually probably helps. It says A and so this can also be A dot not B dot C, like that. So not B dot C is NAND. So we just want A and... Yeah, that works. Okay. So this is how we do it. So we do... Cross out all redundant gates on the diagram above. What? Redraw the logic circuit using NAND gates only. Cross out all redundant gates on the diagram above. The one that... But... What? Well, I wouldn't add the NAND gates. I wouldn't add redundant gates in the first place. Cross out all redundant... No, it says cross out all... So it means cross it out on this diagram. Cross out all redundant gates. None of these are redundant. What do you mean? Cross out all redundant gates on the diagram. Which diagram? This one? Or my diagram? So this is my diagram. A, B, C. So we do NAND. And then NAND. And then we use another NAND to NOT it. And then we get Q. Cross out all redundant gates. So they're talking about my diagram, but I wouldn't have drawn them if they were redundant in the first place. Why would I? Cross. Do they want us to... what? Oh, I think I know what they want us to do, but it's not well explained. So what they actually want us to do, I think, is first convert all of those. So instead of not, we do this. Okay, so that's, instead of the NOT gate, we have that. Instead of the AND gate, B, C, we have NAND and a NOT, right? Now a NOR gate. How do you make a NOR gate out of NANDs? So NOR is X plus Y like that, which is the same as X dot Y dot. Which would be the same as double barring it, which is weird, but that gives us a NAND. So we'd want not X, so that we not again, that we not again. Now we NAND them together. And now finally we NOT it. So okay, so if we're doing this, I think this is what they want us to do. We first turn everything into NAND gates as is. Now we cross out all the NOTs which cancel out. So clearly these two. Clearly these two. And we're left with what we had before. It's the same diagram. Alright, hopefully I've done what they wanted. The following part of a circuit diagram shows an output driver circuit based on a transistor switch. The input voltage of Vin is 1.5 volts. The transistor is just saturated. Calculate the voltage across the 2 kilo ohms resistor. I don't remember how this stuff works. So that's So they're saying that's 1.5. So that's diode, right? So that's 1.4, I think. So this would be 7.6. HFE equals 250. What does that mean? Oh dear. Transistors were never my strong point. I mean, they're bloody important, but... HFE. Got any clues in the formula sheet? No. Across the 2 kilo ohm resistor. So 250. What does that 250 mean? I think it means the volt. Okay, this is. Ugh. It's some sort of multiplier. It's like. It's like the voltage across. Maybe it's something like this voltage is 250 times this voltage. But that would be. Let's just do that. I can't think of anything else. 7.6 divided by 250, but that's going to be very small. Zero 0.0304. It's not too small. 0.0304. 0.03. What was it? 304. So that means there would be 1.5 take away 0.0304 equals 1.4, say around 1.47. Let's just go with that, whatever. Calculate the current flowing through the 2 kilo ohms. So assuming it's 1. So I equals V over R equals 1.47 over 2000 equals 7. 1.47 divided by 2000 equals 0.735 milliamps. 0.735 milliamps is tiny. Calculate the collector current. Collector is which is the collector? Isn't that... So I thought, okay, so I think this tiny amount of current actually goes like this. Doesn't it? Or, I don't know. So the collector current is like that? I don't think I'm using that HFE correctly. Wait, that 1.4 is... That's not what that means. I don't understand any of this. Calculate the power dissipated in the solenoid. That diode is only to prevent current from going the other way, isn't it? So we're not supposed to use that 1.4. We use some of this voltage goes across here and some across the solenoid. HF equals 250. What? It's not even a unit. What could F and E stand for? Let's just sort of cheat. Let's say that we don't know how to do part 3, so let's just imagine it's equals 1 milliamp. So then we can use that for the next questions. Calculate the power dissipated in the solenoid. Power equals IV equals 1 milliamp times 9 volts. But wait, isn't there power across... I don't know. Nine milliwatts? Oh, for goodness sake. That's too small, isn't it? Forget this question. That's a loss. Hotel manager wants to operate. The car park has 100 parking spaces. A ticket is issued on entry and then checked on exit. If the car park is full, then the car park full sign is to be lit. Whoa, okay. List of statements below are missing from the flowchart. After each statement, write the letter from the flowchart to indicate where each statement should appear. Raise entrance barrier. Is car present at entrance? So when would we raise entrance barrier? So is car present at entrance? Yes. Is count 100? No. Give them a ticket. So A should be issue ticket. Damn it. Issue ticket. Has entry been taken? No. Then wait for it to be taken. Yes. B means raise entrance barrier. Increase the count, wait for them to enter, close the barrier. Now is count 100? Yeah, so C will go here. All right, in the other path, is car present? There's no... So either... Okay, so there's no car present. All right. We want to know if, is there car present at the exit? So D is that. And then the last one is just where we decrease the number. E. All right, that I'm pretty confident with. That's a nice 5 marks. MOSFET is a device that can be used to switch on high current loads. The following circuit shows the MOSFET being used to control a heater. MOSFET is just saturated when the voltage across the thermistor is 9 volts. Calculate the current in the heater. Oh, I don't remember. This was GCSE level? I can't remember if it was in my day. So it's 9 volts here, 3 volts here. (2.5S). I don't know what S is. Well, calculate the current in the heater. I don't know. There's no resistance here. You have to understand what a MOSFET does. I don't know what that 2.5 even means. It could be... I think it means some sort of multiplier where you have 2 paths of current flowing, like this and this. It's like if there's enough current flowing here, then it's essentially a switch. But it's a MOSFET, so it's voltage based. Skip this one. After building the circuit, it did not work correctly. Near the temperature where the heater should switch on, the heater kept switching on and off. Draw a modified circuit showing how this can be prevented. Near the temperature when the heater should switch on. Well, this is where you use op amps, isn't it? So if I use an op amp, what do they do again? Don't know. I can't answer these last questions. That's heater kept switching on and off. We want it to just turn on. That's what the op amp is for. No, not op amp. Yeah, op amp. So the minus. So let's say we had this, and the minus, we would just have a fixed input here. And the plus would be what if we put the op amp here? So I don't know. Let's say we do what we did before. But this goes onto the plus, and the minus, I suppose, just... And then... that goes to this. Will that work? But we don't... Okay, let's try that. I don't know. Maybe we'll get at least 1 mark for using a op amp. Op amp is used to produce a hysteresis. Hysteresis? I don't know how to spell hysteresis. I don't even have it in the dictionary. I know it exists. Hysteresis? Maybe that. Effect on the signal to the MOSFET when at the required temperature the op amp will produce a positive output and stay on till the temperature increases to a threshold we control with the resistors. This prevents the heater from turning on and off rapidly. Kept switching on and off. This might not be the problem though. The other two. I think the problem is something else. Something to do with... Let's have a look. So they used this diode before. Should I do the same thing? I don't know. Just copy what they did earlier. Like that? I don't know. Oh yeah, I'm getting tired of this. There's questions I haven't answered, but I don't know what to do about them. There was one... So this is fine. I'm comfortable with all of this. Xenodiode. What is the symbol for Xenodiode? Is it just putting a circle around it? No, it must be something else. I don't know. That I'm fine with. This probably is fine. I'm just spewing nonsense at this point. Calculate the current in a heater. Come on, I gotta write something, right? Like current. Well, let's have a look at the formula sheet again. Ah, what's this? IC equals HFEIB. What is this? Maybe don't need that one. IC equals HFEIB. I might be able to use this somehow. Let's go back to this one. Let's write this down. So we got IC equals HFEIB. B is base, C is collector. Alright, I think this is starting to take shape. Let's get rid of all this crap. The diode is irrelevant. That just prevents alternating. All right, so let's see. Take that out. Calculate the. So we need. So I think collector must be here and base must be here. So IC equals HFEIB. But we still don't. That doesn't tell us anything. Well, how do we know where... Where does current come from in this... Anywhere in this diagram? Is there anything else in that formula sheet? ID equals GM. I don't know what that is. GM, I don't know what GM is, so I can't use that. IC equals HFEIB. That's all we've got. So calculate the voltage across the... Where would we use that formula? Probably here. Voltage across the 2 kilo ohm resistor. I think a fixed voltage is used across the base. We've got 1.5 volts, so some of that is spent across the resistor. So the question is, what is the voltage for if we know the voltage across the base, it's going to be something small. Like 0.7 volts or something. Should I just guess 0.7? Because at least I can get follow through marks. So let's erase all this. So alright, let's say there's 0.7 there. So 1.5 take away 0.7 equals 0.8. It would just be that. It would be 0.8. And this would be 0.8 divided by 2000, which would be milliamps. We'll get follow-through marks. Calculate the collector current. So the collector current, now we can use this formula. So IC equals HFE IB equals 250 times 0.4 milliamps equals... These numbers are looking nice, actually. So 100 milliamps, is that right? Yeah, okay. Let's say it's 100 milliamps. Calculate the power dissipated in the solenoid. Now we're going to get plenty of follow-through marks. We won't actually lose too many marks here if the calculations are correct using the previous power. So yeah, P equals IV equals 100 milliamps multiplied by, what's the voltage? .3? Wait. I don't... I don't know what... Most of the voltage should be across the solenoid. But there must be some across the transistor, right? Or maybe not, I don't know. Alright, let's just say 9 volts, I don't know. Alright, maybe we'll get some calculation point marks. And then this question, GM. We do have GM, I forgot. Alright, we've got this formula up here. ID equals GM times VGS minus 3. What the heck? ID equals GM. ID equals GM. ID equals GM times VGS minus 3. What the heck is that? Let's get rid of some of this stuff. Right. So we know GM is 2.5 S. What's S? Just say 2.5. What's VGS? VGS. It's a voltage across something. D. What's ID? Let's say VGS is 9. Minus 3? Because 3 volts is spent doing something? Alright. Calculate the current on the heater. Alright, let's say ID equals GM times VGS minus 3. Let's say, okay, GM is 2.5 equals 2.5 times, let's just use the 9 volts. 9 minus 3 is 2.5 times 6. Equals 15 amps. It's quite a lot. But that is high current, so okay. Is that it? Is VGS just... So VGS is this voltage here? Because it's MOSFETs, so you work with voltage as the trigger, not current. Alright, let's just say that. And then this, we can just stick with that. Alright, I've got 10, 12 minutes left. Should I just look through it once more? I can't be bothered beyond that. I'm feeling better now. I've picked up a few method marks, hopefully. Latch and delay, yeah, okay. Monostable. B. I don't know about this one. 5, is that what they want? Maybe. Alright. I'm done. Let's grade it. I actually think I did alright. I mean, I definitely lost a lot of marks about transistors. I do not understand transistors. And I definitely remember them being my weak point at school. I was always a fan of digital. Just like assembly code, assembly programming and logic gates, that stuff. So when we had to learn transistors and also signal processing, it wasn't my cup of tea. But it's, I mean, it's important stuff regardless, so it should be in the syllabus. Let's have a look then. Examiners must mark in red ink. Alright. I'll change my color to red then. Oh crap. Oh crap, I numbered them wrong. Okay, anyway, let's change my color to red. How do I even do that? Uh-oh. How do I change pencil color settings? In Foxit PDF editor. View. Comment. Pencil. Yeah, I've got pencil. I hid the bar and now I can't find out how to bring the bar back. View setting. Navigation panels. Why wouldn't you just have this in the... Yeah, this UI is not great. View setting, page display, navigation panels, status bar. How difficult do they need it to be? Digital signatures, document. Customize quick access, customize the ribbon, show quick access. Like I had the thing up where I could choose the color. I closed it because I no longer needed it. And it doesn't appear in the Windows section. Well, there's no Windows section like you have in normal Windows programs. I'm determined to do this. View, form. I can't think what to even Try. I right click on pencil, that does nothing. Help. View. Alright, let's see. Read mode, reflow, boost, rotate. Assistant. No. Read, word count, view setting. This is terrible. No, go away. I don't. I guess we're using blue then. I can't figure out how to change the color. No, there must be a way. Come on. Let me type into the search bar. Change color. Preferences. Yeah, but it's not. I don't need to go to preferences to. Okay. Pencil. Pencil. Commenting. Font. Pencil settings. There's no. I had it. I closed it at the beginning of the stream. Ah, what's this? There we go. Pencil style. Red. There we go. All right. So wrong. 0. 14 is this one, not this one. It goes down on the left and then up on the right. Forgot about that. So, where am I? Need to write down how many marks I've lost. So I've lost 1 mark so far. Now the pen doesn't work. One. Alright, what's next? So we've got 9, 3, and 0. 9, 3, and 0, correct. And OR gate looks like that. Bit wonky, but it's correct. NAND gate looks like that. They also made sure not to include a NAND gate anywhere in the paper, so you can't just use that. 0001 1000, correct. Correct. So it's output, input, process, process. Output, input, process, process. Nice. Easy 4 marks. Oh, damn it. Okay, fine. We've got moisture, light, and not. And we've got delay and latch. Wrong. Delay should come. Of course you need a MOSFET. That last question should have hinted. They literally used a MOSFET with a solenoid. I wasn't thinking. So those 2 are just wrong. You don't get a mark for having delay somewhere in the pipeline. So you get 1 mark for each correct box. 1, 2, 3, 4, 5. I mean, that's not bad, but it's a shame because those are easy marks. So I lost 2 marks there. Monostable. B. 25 milliamps. sorry, yeah. 6, 15, 3, 25 milliamps. 6, 15, 3 milliamps. Yes, nice. So these are where the bulk of the marks are, so I'm not losing too much. Rearranging subs, yeah, whatever. I've done all that really. Red, yellow, brown, gold. Red, yellow, black, gold. Oh yeah, the third color is not the 0, it's the number of zeros. Because it's standard form-ish. So that is wrong. So 3. Forgot about that. Of course, because otherwise how would you, yeah. Otherwise how would you do 20 kilo ohms and so on? Adding resistor in parallel lowers the effective resistance of the power. Yeah, that's what I said. A lower effective resistance gives lower voltage across causes. Yeah, I've basically said that in different words. Four volts. 3 volts? Where did I get 3 from? So I got 100 ohms. I said that in the previous question. Was what I did even correct? I said overall current equals... Six volts. Oh, what I did was just wrong. Because that was for the previous diagram, this one, but not the one where they introduced the load. Oh no. You shouldn't be using current at all. I even said it as I was doing it. Maybe I should be using resistance only and not current. Oh. There's probably no marks there whatsoever. But I did mention the effective resistance of 2 resistors in parallel being 100 ohms. And I believe you can award marks for things which are mentioned in previous questions as long as you're using that. So I reckon I can get at least 1 mark because I literally ticked this box here, 100 ohms. Everything else was wrong, so I lost 3 marks there. Damn it. And that could have been easy. Alright. That's a Zener diode. Also, I got it the wrong way around and it's not in the right place. Zener in series with resistor, 1 mark. Well, I've done that. I just used the wrong symbol. So actually I get 1 mark. As long as I put it in series. So I lost a lot of marks already and I haven't even got onto the scariest questions. Right. 6 quality marks here. I don't like these questions. So how do you... Okay, let's see what they said. The sensing circuit is connected to the correct input of the comparator. So they said swap the two resistors around. I said swap the comparator inputs around. Aren't those equivalent? So I've identified the two problems for sure. So I'm close to 5 or 6. The problem is I don't understand this comparator thing. So I think the thing I said about Lux is completely correct. R1 needs to be increased to just over 25 kilo ohms. That's basically what I said. I said make R1 25 kilo ohms. Combination of R3, R4. So that was right, but apparently what I said about sensing wasn't right. The comparator inputs. Why isn't what I said correct though? Doesn't matter. Okay, so let's say I did recognize the issue though, but I gave a slightly wrong. So I did recognize 2 issues, so it's at least 3 to 4 marks. And basic suggestion of required modifications, but one of my suggestions was slightly wrong. Partially coherent. Well, it's coherent. What I said was coherent. Minor errors or the inclusion of some information not relevant to the argument. So it's definitely 3 to 4. I reckon 4 because what I said could still sort of be right, but maybe there's some reason I forget why it's wrong. But either way, I identified both issues and it was definitely coherent. Let's say 4 then. Alright. Not A, B dot C, and then not A plus B dot C. Yep. And then we got 1, 0, okay, 0, 1, 1, 1, 1. Yep, that looks right. Redraw the logic circuit using NAND gates only. Alright, I see. So I've done this here. And I explained that when I was doing it that I meant for this diagram to be this one because apparently they want... Okay, anyway. 1, 2, 3... 1, 2. This is exactly correct. And then you cross out 2 of those. 2 of those. Yep. I mean, that's correct. And then you end up with that. here we go. I got it right. I guessed 0.7. That was a complete guess. 0.7. Was that lingering in my mind? I don't think so. No, I remember with diodes there's something about 0.7, but I didn't think that was for transistors. Oh my god. That was super lucky. 0.4 milliamps, so that gets that correct. And this one's correct. And this one's correct. Bloody hell. BCAED. BCAED. Alright, here we go, the MOSFET question. This is where I fail. 15 amps. Oh yeah, but that's because I used the formula that I saw. Okay. What the heck is that? Schmidt inverter. I remember Schmidt. I don't remember how to use it though. Reversal of sensings. Okay, no, I did not get this. Explain how your modifications may... Yeah, that's not gonna work. So I lost 4 marks there. Not terrible. I lost 14 marks altogether. So, if I remember correctly, so the total mark is 160. I looked this up for that year. Well, obviously it's 160. The passing mark for the top grade is 130 something, maybe 136, which would mean you can only afford to drop about 24 marks across both papers. I've already dropped 14, so I can only afford to drop another 10 marks. So I'm not on track for top grade, really. But I wasn't predicting top grades. That's okay, as long as I meet my predictions. Oh, I can see my webcam flickering. I haven't set the frequency correct, because it's still set to the Thailand frequencies, which were 50 hertz, but here it might be 60 hertz. Or no, in Europe it's normally 50 hertz, isn't it? Anyway, so that's electronics paper 1. I'll carry on with electronics paper 2 tomorrow, I guess. Yeah, it's interesting. But that is pretty in line with what I actually did at GCSE. I was, now that I have thought about it, I think we did do all this stuff at GCSE. I just forgot a lot about it. Transistors, signal processing. So I don't know what's different about paper 2. I mean, I can have a look without looking at the questions. Oh, can't bring up the folder for some reason. Doesn't matter. Okay.